Hello and welcome back to um, me answering questions from Algebraic Geometry by Robin Hartshorne. Today I am answering question 1.5 of section 1. So let's just get right into it because today is a very theory heavy question. So show that a K algebra B, so B is a ring with a canonical or a an algebra is a ring with a ring homomorphism into K. B is a ring with a canonical ring homomorphism phi from B into A. So we have that definition which we have taken from David Eisenbud's commutative algebra. Now there is another definition which I'm also taking from commutative algebra, which is a ring module M may be described as the module with generators M alpha for alpha in some set A and relations relations eta beta, some beta in a different index set B, if and only if the following is r to the b into r to the a into our module into 0 is a exact sequence. Furthermore, M is called finitely generated if it may if it may be generated by a finite set. Now, for us, what this means is B is a R module, because it is a algebra, which if you want to see why algebras are modules, or well, commutative algebras over commutative rings are modules, go and watch my journals videos. But right now, B is an R module, which is finitely generated. What this means for us is there exists an n here. Oh, and these are like that. What it means for us is there exists an n such that there exists a ring homomorphism from k x1 xn into B, which is surjective. Now, by the first isomorphism theorem for ring homomorphisms, B is then isomorphic to K join x1 xn over I, where I equals the kernel of phi. Just keep that in the back of your mind, and I can change to a different set of notes. So, we're going to prove a different fact. We're going to prove the fact that the quotient rings associated to radical ideals have no nilpotent elements. So, want to show that I radical is equivalent to R over I has no non-zero nilpotence. First, assume I equals the square root of I equals the set of f such that there exists an m in n with f to the m in I, i.e. f to the m in I implies f is in I. Not implies f to the m is in I, that's an equivalence. Implies, well, is equivalent to here, but implies f is in I. And the reason it's equivalent is just due to the definition of an ideal. Now let's pass into conjugacy classes and the quotient ring. So f to the m equals 0 implies that f equals 0 as within R over I. What this essentially means is that any nilpotent element must therefore be 0. Therefore we have shown this direction. Now we are going to show that if an ideal is not radical, then R over I does have non-zero nilpotent elements. So now assume I is not its radical. Then we can find a ring element F within the radical, but such that is not within our ideal. What this means is f to the m is within our ideal, but f is not within our ideal. Or rather, that the conjugacy class associated with f to the m is equal to the conjugacy class associated to 0 equals this, but f does not have the same conjugacy class as 0. Therefore, we have shown by a contrapositive proof that this is an equivalent statement. Now, we can actually get on to showing that a K-algebra is isomorphic to the coordinate ring of some algebraic set in some affine space over affine K space, if and only if it is a finitely generated K-algebra with no nilpotent elements. Well, firstly, let B be the affine coordinate ring for some algebraic set. Well, then B is isomorphic to kx1 dot 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 xn over I of x. B is generated by x1 through to xn, kind of obviously, and I of x is a radical ideal by the Nullstelle Satz. But if we recall from here, I is radical if and only if this has no nilpotence. Therefore, we have shown the only if statement? No, we have the only if statement. Now let B be a finitely generated K-algebra with no non-zero nilpotent elements. We should be able to just choose our generators. So f is finitely generated if it may be generated by a finite set. So there is some there is some n such that there exists a phi from k and x1 dot dot through to xn into B, which is surjective. Now B is isomorphic to k from x1 dot 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 into xn over the kernel of phi. Since it has no non-zero nilpotents, I must, well, I equals the kernel of phi must be radical. Hence, I equals the ideal generated by the zero sets generated by the Nullstellen sets. Well, Z of I is a algebraic set. So, B is isomorphic to K adjoin x1 dot 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 xn over I of, call Z of I x. Then B is this, which is the definition of A of x, where x is a affine algebraic set. Therefore, we have now shown the if and the only if, so we are done. QED quad. No, I'm not going to write the full Latin. Oh no! I've erased everything, but that's fine. I've finished. Thank you for watching. And unlike every other time that I've done this, let me just quickly erase that, because that is a little bit obscene. Unlike every other time that I have done this, I have actually asked my lovely fiancée to draw a lovely little drawing. And this is a lovely big drawing, so we are blessed. Or indeed, I am. So I shall thank you for watching. Or actually, I don't want to detract from good art. So I shall just indeed let me fix my handwriting. Thank you for watching. Goodbye.